is the basically difference between verification and DFT. So in verification, we check about the functional integrity, and in DFT, we check the structural integrity. So earlier, suppose you have a chip. This is some chip. Okay. So there are different type of packaging we have. Suppose one is BGA packaging, but this is called a BGA packaging, and what we use in our college life and digital electronics class, this is called dual line packaging. So inside this, we have our IC, basically main IC core, whatever we want to see. Like then this IC core's output and input will be connected to this course inside of it, and then it will be come out like this, and it will be connected to the PCB. Okay. Now earlier, so we need DFT because in any system design, how you will know that your system is working properly. So for that, you need to do the testing, and that testing should be as earlier as possible in the design cycle. And there was two traditional testing methods, which one is like placing the board on the fixed probe and the moving probe. So basically, you are placing this pin into the board, and then you are checking that data like that. So like there was an issue. Suppose inside of it, the chip like this one, inside the chip is not connected to this pin properly. So you will get you will not get any data output. So it will be basically a dead chip. So to check this issues, we introduce this boundary testing. Okay, so basically, and this boundary testing is introduced from a group that is called Joint Test Action Group. And so it is known as IEEE 1149.1 standard. So if a board, suppose you have a PCB like that, and there are many ICs in between. Okay, those are connected, those are talking to each other. Now there might be a chance that these are not connected properly. So what you will get, like your ultimate, this system will not work properly. This system will not work properly. Now, if you have this IC1, IC2, all these are support this 1149 standard, then what we do, we connect all this in a daisy chain manner. So there will be, like I'll introduce later. So there will be some, it will connect in the chain like this. So this will go like this, and it will connect like this. This will be connected on a chain. So there will be like, so we have 5 pins for this boundary scan. So one will be the TDI. So all the test data input will be going through it, and it will be a 1-bit port, and it will go, all the data will be serial. And these data will be captured on the POSIX TCK clock. And then we have one TMS. So TMS signal is basically, there will be a tap. There will be a tap FSM inside a chip. So for that tap, TMS will program the tap states, and it will be captured in the POSIX of the TCK, and TCK will be your test clock. So it will be running as minimum of 10 megahertz clock, and TDO will be the output. So whatever it captures the data, it will out from this TDO, and it will be captured on the negage of the TCK. Now, TRSTN is an optional pin. Why I'm telling this an optional pin? Basically, you will learn later why we tell it as an optional pin. So it will be an active low reset. So in design, there in the SOC or whatever in the design, there will be various type of IO cells. So some are like digital IO buffers, some are analog IO cells, and some are power supplies. So now we are going to check what is boundary cell. So if you see, this is your IC. So in this IC, we have this TDI, TMS, TCK, and TDO. So TMS is basically the control signal, TCK is the main clock, and the TDO will be the data out, and TDI will be serial input. Now these cells are called boundary cells. So why we put these boundary cells? So suppose you have your chip, and this is talking to your core logic. Now in between, this core logic is not like this. In the after manufacturing, there might be a slight chance that this is not connected properly. So your chip will not work properly. To remove that error, we put a boundary cell in between. So what will it do? It will basically capture the data, and then it will shift out the data. So suppose you are feeding the TDI as different values, and it is not capturing properly. So you can shift out the data, then you can check that the data is proper or not. Suppose you are feeding that 101 and you are getting instead of, and all these are X. So you are getting, suppose instead of 101, you are getting 010. So it might be some short and open are there, faults are there. So in the boundary wrapper, so this will be your boundary cell wrapper. So this wrapper will have the tap instruction register and the decoder and the bypass register and some optional register for future purposes. Now, so the data register, those data register are called this BSCAN are also data register. This bypass register is one of the register, and there will be other register, suppose test data register, which will be used in the further test purpose. I'll tell about this TDR in the upcoming slides. So one thing to check, that boundary scan is not a replacement of the internal scan and or other DFT techniques. It's just a checking of the IOs, that IOs are properly working or not, like properly connected or not. So this is so if you see this small thing, this is the architecture of that cell. So basically it's a input BSCAN cell. So till now, do you have any questions for me? Hello?
Yeah, hello, sir.
Okay, okay. Now, this is a BSCAN structure. So basically, this will be your capture flow, and this will be your update flow. So if you see that this will be your, let me make it bigger. Yeah. So this will be the system pin. Suppose this, you have seen that this these boundary cells are connecting in a chain, something like that. So this will be the input. So this is the input of the system. Okay, this will be feeding, and there will be two BSCAN logic, one marks, and then other marks. Then it's going like that. Okay. So this is that that output pin that is coming from the board. And this will be the other mux input will be from the previous scan, like this will be the previous output of the BSCAN cell, or it will be coming as TDI if it is the first BSCAN cell. And this will be the capture, and this will be the update flow, and this will be the SO. So shift out data will be connected to like this. This will be the SO. This will be the SI. This will be 2, 4. Okay. So the data will shift in, then shift out to the next. Like this, it is connected. Now this update DR and clock DR, shift DR, this will be generated from the tab. So I'll tell you in the later like how the tab FSM is working. So if you see this, so there are okay. Now there are 4 operations. So in normal mode, so in functional mode, basically, uh, how this BSCAN cell will work. So we have to make sure that it doesn't uh, like hurting that functional integrity. Like it's fine that we are thinking about testing of that chip, but we have to make sure that functional specifications should meet in that design. So if you see this, if you make its mode as 0, so whatever it will be work as the functional. So whatever input you will be giving, it will go to this, and then it will go to the, this is the core or main design. So it will go to the design. So this is the functional uh, characteristic of this BSCAN cell. Now, if you check for that scan, so in scan, what it will do, it will take the shift DR will be 1, so it will take the TDI data if it is first BSCAN cell, or the last shift out data of that BSCAN cell. So this data, suppose it will be 1, so it will be available here. So this clock DR and update DR will be coming from the tab. Okay, and it will capture the data, and it will be ready here. The data will be available here. So basically it is working as a scan flow. Okay, and in update, so in update basically we do for the in-test. I'll tell you what are the in-test and all those things later. So in update, the mode will be 1. So this mode will be 1. So whatever data is here, right, in the scan clock, it will be shipped. So, and same thing, that update DS should be pulse. And then the corresponding data will be available here, and this mode should be 1. Then it will go to the core and the capture. So in capture, whatever data is present in the mux 0, okay, then the shift DS should be 0, and it will be captured here. So it is basically called a sample. I'll tell you then what are the sample and the other things. So this is a sample. Okay, so this is how there are 4 modes of the BSCAN cells. So these are the 4 modes, and so we'll talk about what is tap controller. So tap controller is a 16 state machine which controls the whole IJTAG and JTAG process. Okay. So TMS, so its input is like test mode select. The signal controls the transition between the state. So whenever the data, like these are the states, okay. And if you program the TMS, so TMS data will basically help to transition of this states. And this is the data register, and this is the instruction register. So here I have already discussed like what are the data registers and what are the other registers. So instruction register will hold all the instructions. Suppose we have instruction like bypass, sample, preload, xtest, intest, ID code, clamp, IZ. These are the instructions. So these instructions will be stored in the instruction logs, instruction register. So when we want to access that instruction register, we have to go through this. And when we are accessing the data register, in the sense, this bypass register and this BSCAN register, so the tap controller will go through this. Okay. Okay. So if you guys recall that I have told that TRSTN is an optional register. So why I have said that is the optional register. Suppose in tab you are in captured DR or whatever, any state you are in. So if you program the TMS as 5.1, so whatever states you are in, it will go to the test logic reset. Suppose you are in captured DR. So 1, it will go to the exit DR, then 1, it will go to the update, then 1, it will go to the DR scan, then 1, it will go to the IR scan, then 1. So how many ones are there? 1, 2, 3, 4, 5. So whichever state you are in, so if you program the TMS as 5, you will go to the ultimately TMS. Okay. Now bypass register is a part of the data register which are present in the BSCAN or BSCAN. So suppose why we need this bypass register? Suppose you have a PCB. This is your PCB and you have multiple ICs. IC2, IC1, IC3. So suppose you don't want to test IC1, you want to test these two. Okay, but your chain is something like that. This TDI is connected to this, then this TDO is connected to this TDI, and this TDI is connected to, this TDO is connected to its TDI. So you have to go through all this. There might be a different boundaries, boundary scan register. So it will be a huge shifting. So it will take a huge time to shift in and shift out. All those data will go through till IC3. So to reduce that thing, we have introduced one register that is called bypass. So it will bypass all this extra BSCAN what you don't want to test. So it will bypass all those and it will go to the IC2 and then IC3, whatever it is. So what is the architecture of it? So this is a this is a flop, and so this shift DR and TDI will be ANDed with it. So whenever shift DR is 1 and the TDR will 1, this BSCAN cell will activate and it will bypass the whole logic. So here it's a here we have one example. Suppose we have 4 and 4, total 8 8 BSCAN register are there. So if you want to test one pattern on a single chip, so you have 8, 8, 8, 24 cycle will be needed. Now you want to test 2 chips also, suppose chip 2 and chip 3. So still you have to go through all these 8 cells and then it will go, the data will go to this and this. So you have to go through all 24 cycles. So to reduce this time, right, we have introduced this BSCAN. So basically, if we are bypassing all this register, so there will be only one cycle and then 20 and then 16 cycles. So it will total 17 cycle will be needed. So there will be a like the reduction test time will be 29%. So for that reason, the bypass registers got introduced. Now, so these are the instructions set in the tab. Okay. So tab in the instruction register, these are the instruction will be stored. So basically bypass will be same as like in industry, we have a same bypass instruction for each IC. So it will be all one, whatever the length of the instruction register, suppose it might be a 8 bits, might be a 16 bit, I don't know. So based on that, the bypass register will be always all one to access that instruction. And XTest will be all 0, 1, like it will be all 0, 1. Like, okay, binary 1 will be its instruction code. So it will be same for the entire ICs, whatever in the like PCB or this will be one for all. Now, what is the bypass? So I have already discussed what is bypass is doing. Now sample. So sample operation is basically capture operation. So whatever input data you have, suppose one you want to capture that. Okay. So for that, you need to execute this sample instruction. So it will basically capture the data and then it will shift out through the entire chain through TDO. Okay. Now X test. So these are the optional preload and run based. These might be like optional because in some like and the sample, so sample and the preload, clamp, high Z, these are the optional instructions. Why I'm telling this optional? Because in some, suppose there are many IPs in the, like in the SOC, we're using many IPs. Suppose it might be a ADC, or it might be a USB or something like that. So all will have their own. If it is going to the package level, then it will be having its own IOs. Those IOs might not support this clamp high Z. So if your design support those, like if your IOs supporting those instruction, then we will add these instructions also. So mainly I'm going to talk about bypass, X test here, and the in test. Okay. So sample is basically capturing the data I have already told, and the X test. So basically you have your, suppose, yeah, in this, suppose, yeah, suppose you have these two chips in a PCB. Now these two are talking with each other. Okay, these are all connected. Now there might be a chance that these are not connected properly. There might be an open fault or a short fault might be there. So these might be open. Suppose this might be open. This might be a short. Okay. So to know, like to understand or to check that fault, we do the X test. Okay, so we are going to feed the BSCAN some data, suppose 1010, and then it will go to this, and if it is capturing high, low, and it will be shifted out through TDO. Suppose this is TDO and we are getting this high, low logic, then we can tell that it is like it's connected properly. But instead of that, we are getting some other data, low, high, low, then there might be an open or short fault in there. And in test is basically, suppose you want to test your inside logic, the core logic. So to in test, we will feed the data, suppose 101, whatever you want to feed, then it will be captured here, and through the update register, it will be available here, and then we are going to test this, and then through output VSCAN cell, it will capture the data and it will go out. So this is the in test. Yeah, so this is the X test. So yeah, so this is a output VSCAN cell. This is one output VSCAN cell, and this is the input VSCAN cell. And on-chip test logic is called this one. Okay, this one is on-chip test logic, and this one also on-chip test logic, and these are talking to each other. Now, how we'll perform this X test? So first of all, so we are feeding the data through TDI, and these data are shifted in here properly. Okay, through the shift DR one and the clock DR. So clock DR and shift DR, clock DR and shift DR will be generating from the tab, and through update, it will come like this data will be available here, and through mode one, it will go to here. and then we will do the capturing of the data. In the here we want to capture the data. To capture the data, shift will be happening, and this will be captured the data, and the data will be out through this from the TDO. And if you get 0 0 0 instead of high low high, so this is a shoulder defect. We will find that where is the particular defect. Okay, so now how this X test is working in the design. So I have told you that to go to the test logic reset, we need to do 5.1. We need to program this tab with the 5.1. Now we are going to program it, and we are going to a test logic reset. So after that, we are going to load the instruction. For that, we need to go through that IR, instruction register. So now we are going to feed it 0, then it will go to the run idle state. Okay. Then we'll feed it 1, it will go to the DR, then 1, it will go to the IR, then 0, it will go to the capture, then 0 shift. So when we'll go to the shift, okay, we will feed that, suppose, okay. So why I have kept this 7-bit? So suppose we have two, yeah. So we have two ICs, okay. So one IC have instruction register of 4-bit, okay, and one have instruction register of 3-bit. So all 3 and 4 will be total 7 bits. So for that reason, we took the 7-bit instruction register. Now we are going to feeding the, so it's in the shift IR. So in shift IR, what we will do? So shift IR, we are going to feed the TDI value into the instruction register, and we will load the X test value as all 0. So here we have kept that instruction as all 0. Okay. So that data will go to the shift register, and the shifting will happen 7 clock cycle, because the IR bits are total 7. So it will shift in the all the instruction, and after shifting complete, we'll go to that update, and then it will go to the ideal state. So this is capturing, so it will load the instruction X test. Now we are going to feed the data. So tab is in the X test instruction. Now we are going to feed the data through TDI. Now, so now the state, it was in run ideal state. Now from that, we are going to feed the boundary scan with the data. So then we have to go to the shift DR state, where we are going to shift in the data. So while we are in the shift DR, so it will assert that shift DR signal of the BSCAN cell, what we have seen here. So this is the shift DR. This will be coming from the tab. Friend. Pen is not working properly. So yeah, so we are going to feed the data as 101 in the, so we are keeping the all X because we don't want to test all those IOs. We just wanted to show one example with 101 data. We can feed a different data. So why we have kept this 16-bit? Because the total length of that boundary scan boundary scan register is 16 because 8 are here and 8 are here. So total are the 16 bit bound data register we are forming. Now we are going to feed the data 101. Suppose this data is 101 is loaded here, and then after loading that data, so all the data is loaded in the BSCAN cells. Then we are going to do that one. It will go to that exit DR, and then so it will stop its shifting, and then it will go to the exit DR, and then will feed another one. So it will go to the update, and after that it will go to the select DR scan. Now, whatever data we have shipped in, we are going to capture that, and then we are going to shift out. So to do that, so it was in scan DR, select DR scan. Earlier state was it. So now we are going to feed that TMS as 0. So it will go to the capture. And then we are going to feed another 0 to the TMS, and it will go to the shift DR. Okay. So it will go to that shift DR in here. So it will be available here. And then whenever shift DR, so it will be in the shift DR state. So it will be shifting out the data through that SO. Okay. So it was that end of that X test. So basically what we are doing, we're just shifting in the data through the TDI, and we are, so basically we are shifting in the data through TDI, and then it will be available. Is it?
Removed it like VLSI for all. Like,
hello.
Yeah, you can continue.
Is it? Okay. Okay. So basically, the summary of it, you are going to feed that data through TDI, and it will maintain that data. And then when we are doing the update, it will go to that. So it will go. So basically, you are feeding the data through TDI, and then after doing that update, so it will capture all those data, and then you are shipping out through TDI. So this is a basic X-test operation to check these lines are like these connections are proper or not. Now sample I have told like this is a basic capturing operation. So whatever data is present on the input, okay, you are going to shift it out the data. Suppose you are feeding like these are the inputs of that chip. So these are the data are there. So you are capturing the data into these BSCAN cells, and then you are basically shifting out through the TDO. Okay. So how it is happening basically? So so in the shift DR, it should be 0 to capture that input, and then the clock DR will be pulse, and then that through SO it will go out. Okay. And it will be same as the output side also, like whatever data present in the core, it will come out, and that capture flop will capture that, and it will go to that SO, and through TDO it will come out. So how this capture operation is happening basically? So in the TMS, we are it's in the run idle set. So first of all, you have to do that reset. So you have to make it all one, like all 5 ones in TMS, and you will come to this test logic reset up. Then what you have to do, you have to program that one to go to the DR state, and 0 to the capture. So in capture, all the data present in the input side of the BSCAN cells will be captured in it. And then you will do that shift operation to capture, scan out the data. So that is basically happening here. Now, we are going through like what are the like. This will be the, so whatever I have taught earlier, it will be a basic understanding of the BSCAN. Though I didn't cover the whole thing because that BSCAN is a huge thing, and we'll go through that how we'll do BSCAN in the industry. So basically, in every package, suppose whatever I have told, package in the sense, these package, it will tell us the pin order. Okay, so it will have those pin orders. So we need that pin order, and we'll need a design. Basically, in RTL or netlist, we need that one, and the libraries. So if you use Mentor tool, then you'll need Mentor libraries. If you use Synopsys tools or Cadence, it might be different tools. You'll need a libraries for each tool. I'm not talking about TSMC library. I'm talking about tool-based libraries of that IOs. So every tool will have their different IO libraries, different format. And then you have to do the DRC. So you need to check that design rule, check that whatever BSCAN cells you are inserting, right? Those should be following that proper design rule. It shouldn't break the functionality of the design. Then you have to create that specification. Specification in the sense you have to make sure that these instruction register are not interfering with other instructions, and these are not breaking that proper DFT rule and all. And extracting that equal, this is a mentor kind of mentor tool related thing, ICL. So that I'm Rajat, should I tell that what is ICL or something like that, or should I not mention those? Hello. Okay. So those will be equal, and then creating the pattern. So it will create the TB and the STIL and WGL. Those are the patterns. Now, as a DFT engineer, there will be another thing. Suppose you have to design your BSCAN. There might be different working areas of the BSCAN. Suppose you have 50 BSCAN cells. So okay. Mhm. So as a DFT engineer, you might have to design that BSCAN architecture as well. Suppose you have your design that have 50 to 70 IOs, and you want to you don't want to, suppose this is a chip, and this will be the east side, this will be the north, this will be the west, and this will be the south. So east will have 30 BSCAN cell, north will have might be 5, this will be west will be have 5, and rest of the others are in the south. So you don't want to test the south logic, so you can just bypass it. So for that you have to uh, change your tap instructions and all to proper architect this solution of the BSCAN. So that's all from my side. Interviewer might ask this type of design questions. Suppose I'm just giving you one example. Suppose you have your SOC, and in SOC you have your east IOs, north IOs. This will be the west. This will be your west IOs, north IOs, east IOs, and south IOs. Okay. So suppose you have one SoC which has 80 IOs. Okay. So 20 IOs here, 20 IOs here, 20 IOs here, 20 IOs here. So now in design, there might be a chance that in package level, there might be a different IPs. Suppose all IPs are from different vendors, and now those IPs have some high speed IOs, some has like low speed IOs. So some support. So I have told like here, like some don't support high Z, some don't support clamp, some don't support sample. So suppose you have like that. So suppose your these 20 IOs doesn't support clamp. So how you will make that chain that like you want to only test 60 cells in that for the sample, and this 20 doesn't support. So how we will make that architecture that it will not hurt these 20 IOs at the time of the sample test. So there might be one thing like you can do separate instruction. So in the instruction register, you might make one different instruction called as like bypass 20 IOs. Okay. So in that bypass IOs, you'll make a like mux, and then TDO will be connected to this mux, and then like this SO output will connected to the mux, and other output will connected to this mux input, and then this output will go to the SO. So those like it those 20 IOs will be tested through here, and it will, and these 20 IOs will be bypassed. So this is how you can make a architecture, different kind of architecture. Now in, if you go further, like there might be other design challenges. Suppose you have two different BSDL. So in BSCAN, BSDL is a mandatory thing. So BSDL contains the pin uh, port input output namings, and pin description, what are the ports specifications. Suppose like it's an input pad or output pad or a bidirectional pad, and it will also contain which what are the what are the instructions in it, and what are the pin mapping, so how it is connected to the package and how it is bringing up to the package level. So all this information will be in the BSDL. So it might be you will receive a separate BSDL and you have to merge it. So you need to understand the BSCAN, BSDL also. Like only knowing the BSCAN will not help you. So in BSDL will there will be a description of the package. So what is the package name? It might be a BGA packaging. It might be some different kind of packaging. All those things will be information will be there in the BSDL. So yeah, these are the some, like I have discussed one or two design problems. There might be a plenty of design problems that we can come up with, and yeah, this is over of that BSCAN. So yeah, I'm done with my PPT and the some interview questions.